Hello, everyone. Thank you very much for coming to the first Green College Resident Members Series talk of the 2023-2024 academic year. My name is Michael, and over here are Riku and Michi, and we are the co-chairs this year of the series. And I am very delighted to introduce our first speaker. Pedro Villalba González is a Spanish PhD student. He is the Rafael del Pino Scholar and La Caiza Fellow in the Department of Physics and Astronomy at UBC. He is working in observational cosmology in the deployment of a new radio telescope, the Canadian Galactic Emission Mapper, which will help us search for gravitational radiation from the very early universe. And today he will be talking about advancements in this work and in this field. I should also note that it is a tradition in this series to start the series with a first talk that you know is going to be really excellent and one of the strongest in the series. However, this year, Pedro was actually the only person available to present this early in the semester. So we'll see. I'm just kidding, I'm sure it will be excellent. So please give a warm welcome to Pedro.
Well, hi everyone. I'm gonna try with this, but maybe not. Can you hear me well? Maybe this works with the audio. I can just put it. Okay. Well, before starting, I'd like to begin by acknowledging that the land on which we are gathering tonight is the ancestral, traditional, and civic territory of the Musqueam people, and that I'm thankful for having been given the opportunity to live here, study here, and have an incredible community here. The title of the talk is Unveiling Cosmic Origins, the Inflationary Universe. I couldn't come up with a catchy topic, so I told ChatGPT give me a few topics for inflation. And it started saying things about the economy that I didn't understand, but at the end I found something like this. Thank you. And yeah, well, I'm gonna just, even though Michael's fantastic introduction, I'm gonna give a bit of an overview of who I am. I'm a first-year PhD in the observational cosmology group here at UBC, and this is how I look when I work. This is how I look when I'm not at work, and that's what I enjoy the most. And this is an old picture that I always saw with my parents, who are in Spain. I really need to update this. I was 19 here. I look even younger. I'm from Spain. I'm from concretely from the south of Spain. If you've had one conversation with me, you know where I'm from. I'm from the most beautiful city in Spain, and probably in the world. The Alhambra with Granada, which has the Alhambra, which is this old monument that many of you might have heard of. That's where I grew up. And that's where I got my undergraduate degree in physics. Okay, enough of me. Has anyone here heard talk about inflation before? What have you heard about inflation? What? What did you say? Okay, this is all the economy inflation that you're going to have tonight. I'm sorry. This is not what I'm going to talk about. It took me 2 hours to select these memes, so I hope you enjoy them. This is the slide that took me the longest to prepare. Today I'm going to talk about cosmic inflation, which is this cosmological paradigm on the history of the universe. Much boring than the other inflation. But before jumping into that, I have the perfect plan for a Monday night, and this is a picture of Alhambra for your entertainment. I'm going to start by talking about how cosmologists and scientists in general understand the universe with some of the tools that we have in our hand. I'm going to move on to a very brief history of the universe, which is also known as cosmology, and that's what I try to do for a living. I'm gonna move on the cosmic microwave background, and if you lived here last year and you came to my talk, you probably have heard a lot about it, so sorry because some of the slides are the same. There are a couple puzzles that appear when we look at the cosmic microwave background, and I'm gonna talk about a solution to those puzzles, and the solution is inflation. And I'm gonna talk about how we can search for inflation, because even though it's a really realistic, well, I wouldn't say realistic, but really feasible paradigm for cosmology, why we haven't found, there is a signal that we haven't found yet. And that's going to be towards the end of the talk. And then I have some conclusions in which I anticipate a meme that all of you have seen already. But before, I know that Michael said that talks will be 25 minutes, 30 minutes, and lots of questions. I'm the first one, so I'm going to not obey that rule. Probably this one is going to be a bit longer, but please interrupt me whenever you want. I'm not, if we don't have questions at the end, it's fine. If I don't cover up to 0.5 or 6, please interrupt me whenever you want. An old professor of me said at the beginning of every class, stupid questions do not exist, only stupid answers exist. So please, whatever comes through your mind, just raise your hand and interrupt me. All right. Does anyone have an idea of how we can understand what is out there? What can we use? Telescopes. Our brains. Okay. Good. Exactly, telescopes. Through history, humankind and any civilization on Earth have been looking at the sky and trying to understand what was happening through different ways and engaging with it in very different ways, and that will give place not only for a talk, but to an entire course on the history of science. I'm not going to focus on that. I don't have the knowledge, honestly, to do it. I'm going to focus on one of the first times, if not the first time, there is some historical discrepancy here, that a human used a telescope pointing at the sky and learned something about it. And that was Galileo Galilei. He turned his telescope to, I think it was to Jupiter, and discovered 4 moons. And ever since then, humanity has been just building larger telescopes with just the aim of being able to point deeper in the sky and to be able to resolve images in a better way. This is a picture of the Herschel telescope, which is a 1.2 meters telescope that was made in the 1797, so it was 18th century. And this is a picture of a really recent picture from the very large telescope in the European Southern Observatory. As you can see, we are really original. Yeah, almost as original as me with the title of the talk. This is just what we've been doing for almost 400 years. Nowadays we have other technology. There is also the very large array, which is this system of antennas in New Mexico, and a telescope nearby, CHIME. These are just 2 examples. This is actually 5 hours away from here, and these are like huge. There are like 1,000 antennas there. But this uses another technology, and the technology that it uses is the same technology that we use to tune in CBC radio, for example. What this is a radio telescope. So instead of just looking at the light that we can see with our eyes, we look at radio waves that come from all over the space. The good thing of doing this is that we can learn many different things. So I don't exactly remember what object this is. I think this was a nebula. I honestly don't remember. But the point is, these 2 images are pointing at the same part of the sky. We are just looking at it with our eye and with a radio telescope, and we see how much information we can get from the radio, whereas with the optical we will only get that. This might seem super complex and something that only astronomers do, but actually it's the same physics, exactly the same physics that there is in the infrared cameras. If I look at this person on the left, I can see that there is just a person holding 2 glasses. But if I put an infrared camera and I look at the infrared radiation coming out of them, I can see that there is a glass that is warmer and a glass that is colder. So this is infrared. I said radio, and then visible light. These are all a manifestation of the same phenomena, which is electromagnetic waves. Electromagnetic waves are just waves that travel at the speed of light, and the only difference between them is the size that they have. So radio waves are huge. Radio waves are from meters to hundreds of meters. The visible light that we see is tiny, is in the order of 500 nanometers, more or less. And we have X-rays, which is also another electromagnetic wave, gamma rays, which is this thing that comes out of radioactive nuclei, and microwaves. An example that I like to give on this is, if we go far away from the city and we look at the galaxy on a very dark night, this is what we will see. We will see the galactic plane here, and we will get these stunning pictures. But if we actually had detectors at many different wavelengths, this is how it would look like. And this is not a simulation. This is an actual composite of images, all of them pointing at the galactic plane. So we really have a huge window to the universe. Now, I'm surprised that no one has stopped me yet. I don't want to run through this really fast. I have a question for you. Does anyone know what will happen if the sun suddenly switch off? And if you have a physics degree, I know you know. Yes.
8 minutes?
Yeah. And why 8 minutes? Exactly. That's how much it takes any electromagnetic wave. But yeah, exactly. That's exactly the point. This is a very poetic sentence that I like to say, even though no one likes it. And it's our eyes are looking into the past. So whenever we are seeing light, and when I say light, I can say other also radio wave, an X-ray. We are looking at something that was emitted some time ago. So if the sun all of a sudden switch off, it will take us 8 minutes to notice, because, as Evan said, that's the time that a photon of light will take to reach us from the sun. If we had a laser pointer in the center of the galaxy, it will take 28,000 years to reach us. And the center of the galaxy is not that far. If we look at cosmological distances, that's nothing. There are like clusters of galaxies out there. So if we want to learn about the past and the history of the universe, what we need to do is to just look farther, to just keep looking far, far away, and we'll be learning about how the universe was when it was younger and younger. Just for context, the universe has 14 billion years old. It's 13.8 is our most recent estimate, and we can learn a lot in all this time. So if we start looking at things that are far away from us, we have first our solar system. Then we have our nearest stars, and the nearest stars other than the sun are Proxima Centauri and Alpha Centauri, I think. Yes, and they are like 4 light years ago. 4 light years ago is a lot of time, but still in cosmological distances it's not that far. It will only take 4 years. We are only seeing how the universe was 4 years ago. That's not even a legislature. For the galaxy, we have our own galaxy. We will have a bunch of stars there. This will take, as I said, if we look at the center of the galaxy, 28,000 years. But then we could look at galaxies that are farther away from us. And we could keep going. We have this whole line is 14 billion years in total. We could just keep going, but there is at a point at which we will need to stop. And that point is when the universe was 300,000 years old. So it's basically as if you look at a person that is 80 years old, and you look at a picture of how they were when they were 2 hours old. Why? Now instead of looking, I know I shouldn't do this, but instead of looking to the universe in reverse, I'm going to look it from the beginning. Our cosmological model, the Big Bang model, says that the universe started being really hot and really dense. Everything was together basically in a plasma, And as it was cooling down, things started to separate. So in the very beginning, we had all the particles, all the electrons, photons that are these electromagnetic waves all together. And as it was cooling down, there was a moment that they separated. And the moment that they separated is when the universe was 300,000 years old, because that's when it had cooled down enough to separate. And at that moment, there was a huge amount of light, a huge amount of electromagnetic waves emitted all over the universe, and that's what we know today as the cosmic microwave background, which is just this light of it. People have referred to this picture as the face of God. I don't really know why, but I like to call it the baby picture of the universe because it's literally as if we were looking at a baby. Sorry? Yes?
Sorry, I'm confused. Why is there a little flappy thing in the picture?
This?
Like, what is the blue, what is the purple thing? Yeah.
This?
Yeah.
Oh, this is the cosmic web. That's the way that galaxies are structured. So galaxies are attracting each other, and it's been theorized, and it's actually been observed that they tend to cluster following this kind of, it looks kind of like a neuron, allowing for some regions that are called voids there, in which there is a really low density of galaxies, and some other regions which are more dense.
So that's like a simulated version of expansive.
Good. I'll touch on that very briefly, because that's the, from here, if you let that evolve on time, that's what you see. So these small points that you see here, with time propagate and form this structure. That's a really, really good question. This is a picture of the cosmic microwave background. Before going in, is everyone familiar with these kind of maps? 100%? Okay. This is called a mole-wide projection. The sky, we can see the sky has something that is just a sphere on top of us. If we want to project a sphere into a plane, there are many ways of doing it, and you all have seen maps. There are many ways of doing maps. The way that we like to do it in cosmology for mathematical reasons in the analysis of the maps later on is called a mole-wide projection, and it looks something like this if we did it with a map of Earth. So it's as if we take this sphere and we just project it this way. So if the Earth is here in the middle, and please ignore the content of this map, if Earth is here in the middle and we see the sky has this celestial bolt on top of us, this is how it will look like. So in other words, this is a way of uniquely labeling a point on the sky without having to worry about where the Earth is, what time of the year is. Yes?
Is it an assumption that we know the universe is a sphere? Or is that
So, the universe is flat. The universe is not a sphere. What is a sphere is the sky. So when you look at the distances are so big that you can just imagine that when you do maps, you can just imagine that everything is at the same point. So you are taking something that is three-dimensional, has the universe, but the sky that you see from Earth, the map of the sky is two-dimensional. So it's as if I take a picture of here. This is really a three-dimensional thing. If I just take a picture, I can uniquely label where each of you are. I don't have information of how far you are from me, but I still can, if what I'm interested about is are other kind of things, that's fine with us. Yes? Oh, okay. It's imagine that you were doing. Have you seen these maps of the sky with constellations on them? Those stars are at different distances from us. So some of them are closer to us, and some others are farther away from us. And we know that by the amount of light that we receive. Imagine that you don't care about that. You only care about the shape that they have. If you only care about the shape, you can forget about how distant they are, and you just do a drawing and you just draw them as 4 lines. That's the same thing that we are trying to do here. Any more things? Okay, so, sorry. The picture that I showed before, even though it has this, really colorful scale, in reality, that picture is super uniform. It's uniform in 1 to the 10 to the 5, which is almost a million, 100,000 times. So the scale chosen here, if this is something like 3 Kelvin degrees, which is minus 200 something Celsius, these small differences between them are only in the range of micro Kelvin, which is really, really few, and sounds like a really strange coincidence. What this is saying is that if I look at how the universe was when it was only 300,000 years old, it's incredibly homogeneous, and that's a coincidence. Why? Why there would be no reasoning to think that that's the case? But that's what the cosmic wave background is telling us, and that's what happens if you look at the distribution of galaxies all over the sky. That's what happens. It looks quite the same. Even though locally we can see how, there is a galaxy, there is a void, there is a cluster of galaxies. If you look in the really big scales, that's what is happening. So this map, this cosmic microwave background, these small scales, these small differences that I was talking about, represent colder and hotter parts of the universe at that time, or what is the same, more denser or less dense parts. What happened, and answering to the question that Mina said before, what happened with this is when the universe was 300,000 years old, it was a bit more dense in this region and a bit less dense. Sorry, it was a bit more dense here and a bit less dense here. As we propagate through time, that means that due to gravitation, there will be more things coming to the dense region and less things going to the larger regions. And we've seen this correlation. So you can take this map and correlate it with the distribution of galaxies on the sky, and that's something that we see. So basically, we can learn a lot. Actually, scientists know the age of the universe by looking at this map, know how much dark matter there is in the universe, how much dark energy there is, know basically almost everything that you can see in cosmology can be learned from here. Yes?
This is a huge tangent. You said represents quantum fluctuation.
Yeah. Oof. So the universe started being concentrated, being really hot, and in a plasma, being a plasma state. So we can see it has been homogeneous. Being homogeneous up to a point, and the fluctuations, those fluctuations happen at a quantum scale, so that's why we call them quantum fluctuations, and that's what propagated until it was 300,000 years old. So imagine that you have this table. This table is red, but if you look really close, there is a mark here. There is another mark there. Imagine that those marks were caused by something quantum, that everything was in the quantum regime at that point, and that's why they are called quantum fluctuations, because it's something that happened in the really, really early universe. It's not something like a galaxy or something. And there is also a note to do here, and there is roughly the same number of hot and cold spots, so basically roughly the same number of orange and blue regions, what means that the universe is normal in a statistical sense. This is compatible with just being taken from a Gaussian distribution, so we can do a bunch of statistics and a bunch of mathematics from here. I said that there were three puzzles with this map. The first one I kind of hinted at it already, and it's called the horizon problem, and it's, I will say, the most mind-blowing for me. If we look at this map, and as we said before, the speed of light is finite, we know that this was emitted almost 14 billion years ago. Still, this point and this point, there is no way that light could have traveled from here to here in that much time. There is no way. Actually, any point farther away from each other from 2 degrees, there is no reason that when the universe was only 300,000 years old, they could have been in, it's called causal contact, but that just means that light can go from one place to another. Light is the thing, is what travels fastest in the universe, so there can be no information exchange in that time. I like to do an analogy that probably is not the most correct one, but imagine that you have a swimming pool full of cold water. If you pour hot water in one end, if you wait long enough, you'll be able to see it propagate through the whole swimming pool and there will be some equilibrium reached. But if you put hot water and at the same time you measure the temperature on the other side of the swimming pool, you'll see no difference. So if these points couldn't be in touch with each other, why are they? How come they look the same? We think that the Big Bang theory just says that everything should be random. There is no reason to believe that there should be some preferred direction. The second problem is the fact, yes. Sorry? If yeah. So what we are saying that the universe was normal when it was 300,000 years old. There is no reason to believe that it was not normal before. Actually, that's one of the things that inflation explains, and I will touch on that a bit later. And right now, just by looking at the distribution of galaxies, we know that also everything looks quite homogeneous, and all the fluctuations that we've seen are normal, are Gaussian fluctuations. There is a field on the study of non-Gaussianities in the cosmic microwave background, which is people looking at things of non-normal distributions there. I'm not an expert at all. I know there is some work being done there. Oh, because there wouldn't be a driving force to change that. So if we say if we just let the universe evolve, there shouldn't be something. I cannot think of a physical mechanism that will make that change towards a preferred frame. That's maybe more that's a philosophical problem in physics. I don't remember right now the name, but it's the fact that when we do cosmology and when we do physics, the first thing that we say is that the universe is isotropic. So basically that it's the same in all directions. That's something we don't know because we cannot explore the whole universe. But that's something that we have to that's something we need to impose in order to do our theory. Yes.
For me to understand this puzzle, so you're saying that if light can reach further than those small circles, then why is the universe so
Yeah. So if light cannot travel farther away from those circles, how can it be that the picture looks the same? Because light traveling from one point to another sets the barrier at which information can travel. So imagine that there are like 300 people showing up to a party. None of them talk. Why? Wouldn't it just be a coincidence? And now imagine that with the huge distances. So if it was by chance, this would be a really, really small chance. Yeah.
In this circumstance, what is meant by information traveling? Just light?
Yeah. Information, it's just light. It's just a message. So if I'm talking about causality. So what I'm trying to say is that there is no causal contact, no thermal contact between them. And that's just the fastest way of sending information is light. Okay. Our second puzzle is the fact that the universe is flat. If everything is random, the evolution of the distribution of matter and energy itself, this is the math that there is behind the geometry of our universe, says that we should tend to have either a closed universe, so either a spheric universe, or a hyperbolic prefer for it to be flat. Actually, for it to be flat, these fluctuations that I was talking about in the cosmic microwave background should be fine-tuned to 1 into 10 to the 62. So there is a 10 and 62 zeros later. Almost has the number of emails that you've received from me, but way more. Sorry for the non-resident. So there is no way that can be like, how can it be so big of a coincidence? And if that was not enough, there is another puzzle. Do people know what electrons are? Okay. What are they? What are them? This happened this morning with my first years. No one replied later. Yes.
The negative portion of an atom?
Yeah, okay, it's a unit of, you said that it's a unit of electric charge. It's one of our fundamental particles, but what I was looking for is the unit of charge. We have protons that have positive charge, and it's just one positive charge. But when we look at a magnet, we cannot have that. So if you have a magnet and you break it, you have north and south pole. We know that electricity and magnetism are two faces of the same coin, and there is no reason for something like a one-pole particle, called magnetic monopole. There is no reason for it to exist, to not exist. Physicists have been looking for this for at the very least 200 years. No one has found one, and if you have one, you have a trip to Sweden to receive a Nobel Prize, and you'll probably be quite famous. If you look at the theories of the Big Bang, called grand unified theories, all of them predict the existence of monopoles, but it seems quite obvious that they should be there. So why haven't we found them? Yes.
Sorry, can you again what a monopole is?
Yeah. So an electron has positive charge, and it's just one positive charge. And it has, if you look at it, it has if it was repulsive to everything. To everything that's not a good picture anyway. To everything that is that has a positive charge. If you look at a magnet, you have a north pole and a south pole. So if you have other magnets, you can align them or make them repel. But you cannot have only one magnet that only repels. So one side will repel and the other side will attract. There is no such a thing as a magnetic particle that repels or attracts. That hasn't been found yet. There, I saw other hand. No? Okay. And they are predicted, the theories constantly predict that they should exist, and there is a huge search for this. So where are them? The solution that people found was inflation. And inflation was a theory posed in the 1980s by Alan Guth, who was a postdoc at Princeton that was almost going to be fired because he ran out of ideas, and he suggested a solution to these three problems with a period in the very, very early universe. And when I say very early universe, I mean when it was 10 to the minus 34 seconds, which is 0, 34 seconds, 1. Really, really, really early universe. And what he suggested is that at that time, all this, the whole universe underwent a period of accelerated expansion in which it expanded by e to the 62, which is something, I don't remember the number of orders of magnitude, but I think it was 10 to the 28 orders of magnitude, which is incredible. So that's inflation. There is no thing about money being more cheap or anything. That's what we know as cosmic inflation, and this one is up to now the most solid cosmological paradigm, I would say. And if there is a theoretical physicist here, please ignore this, because they hate it. But this is what we have at the moment as a robust model to explain the universe. It solves these three puzzles, and it does it, I think, in a really elegant way. The first one, the fact that the horizon problem, the fact that the light couldn't travel that fast, is if you have the universe undergoing this huge expansion, maybe points that were in, you can have points to be out of contact, but that were once in them, and after this huge, after this rapid expansion, they are not anymore. So it's all of a sudden they are just never in contact. Again, the flatness problem solves it by saying, okay, any curvature possible in the universe has gone away for this during this expansion, during this event. And the monopole problem solves it by saying, wait a minute, there are monopoles, just that after inflation their density became so small because of this huge expansion, that it's not that there are not, it's just that we cannot detect them. Out of these three, we know that the universe is flat and that we've measured really, really accurately, and we keep getting measurements of this. The flatness problem is an explicit prediction of the theory. So if someone tomorrow came up and said, oh no, the universe is not flat, you've been doing your data analysis wrong, this theory will be worth nothing, and I probably will need to move to consultancy because I couldn't do physics anymore. But okay, if this solves everything, and this is what explains the whole history of the universe, why are we still debating about this? Why are we still talking about this? And sometimes we get in the news things like, oh, scientists reveal the beginning of the universe. The reason is that we haven't been able to convince ourselves that inflation happened. And if I play a bit of devil's advocate, it's hard to believe. Because in order for inflation to happen, we will need to accept that the physics that we understand nowadays were valid 14 billion years ago. And we have no reason to believe that. We have no evidence that that was indeed the case, especially at the energy scales that this work. It's as if I was saying that Newton theory, the Newton gravity, the one of the apple falling, it's as if I say that that theory is valid in every scale. We know today that that's actually not true, and general relativity, Einstein just gave us this theory in which it extended this our previous understanding, and then we could prove it because we had access to those energy scales, but we have no reason to believe that that was the case. In any case, this is the only theory that almost the only theory that survives, and many of the predictions that come from there are okay in the observational cosmology point of view. So all the small fluctuations in the CMB are well explained by inflation, the fact that the universe is flat, and some other things are well explained. But there is one thing that it's a really explicit prediction that hasn't yet been found, and that it's, I would say, the holy grail of cosmology. There are people who like to call it, and it's a signal, a pattern in the cosmic microwave background, but we haven't been able to find it. If inflation happened, this is if there was this huge release of energy at the very early universe, there would have been gravitational waves that would have been sourced at that very moment, and these gravitational waves would have traveled, are called primordial gravitational waves, and they will have traveled through the whole universe until they get to the point that the cosmic microwave background is emitted. At that point, they will have left an imprint in the geometric orientation of the cosmic microwave background. And when I say geometric orientation, I'm talking about the polarization. You can ignore this slide, but all I want to say is if you have a wave coming to you, apart from when it's coming to you, one of the things that it has is orientation, is the direction that it's following. You can have a wave being linearly polarized, and that's something has what happens. You look with polarized glasses at the sun, you can have something circularly polarized. Well, if you do the math, what was predicted was that these primordial gravitational waves could have sourced polarization in this way, in something called a B mode. So if you look at the polarization of the cosmic microwave background, you can have either a E mode, E, or that comes actually from electric field, or B from magnetic field. This one we have found, and this one gives a bunch of information about other stuff, but this one we haven't been able to find yet. And we know that the only physical mechanism that will source this are gravitational waves from the very early universe. This is how a cute map of the polarization looks like, and what we are looking for is for a pattern as the one I just showed here, but hasn't been found yet. There is right now a titanic effort in the search for this signal. A lot of money from taxes are being spent on this. There are many telescopes looking for this, especially in the South Pole, not because they like the cold, but because they have the driest skies. And to look for this kind of signal, you need something that is not humid and something that will not perturbate your measurement. Out of all the experiments, one of the most important ones, and not because my friend worked for it, but because it's actually the one that is closest to finding it, it's called BICEP. And actually the electronics for that telescope were developed at my lab by my friend Sofia, who might see this at some point. So hi, Sofia. But yeah, people have been looking for this for 30 years. We still don't find it. Why we don't find them? There are many issues to this thing, to looking for this. First of all, looking at the cosmic microwave background is hard, because you are looking at whatever is farthest away from you. And apart from that, it's quite faint. There is also the problem that when you have light coming from that far, when it comes to you, basically anything lenses the light. So that means that the gravitational field that a galaxy has or big stars have will curve the light, and not only that, they will also affect the polarization. The main problem, I think, is the foreground problems, and it's the fact that, as I was saying, anything between us and the cosmic microwave background is contaminating our view of it. So it's the same thing as if you look through a window and it's full of dust. And one of the foregrounds is literally dust. It's dust from our galaxy. So if you have your detector here and the cosmic microwave background really far away, first the polarization, this geometric orientation is really faint. It's not intense. But not also that, you have foregrounds, and the main foreground is our galaxy. The galaxy is strongly polarized, not so important for us. It's been relatively well characterized, but not well enough. Quickly, this each of these colors is an astrophysical component. It doesn't matter which one. It's just components from our own galaxy. If we look at only the intensity, this is the light that is coming from us from the cosmic microwave background. There are a lot of components there, but this light blue curve is the cosmic microwave background. There are some frequencies, some wavelengths, at which is brighter than any of those. So that's why we have good maps of it. But if you look at the polarization, which is this here, there are not that many components that are polarized, but all of them are brighter than the cosmic microwave background. And not only that, this polarization is the E mode, is the one that we've been able to find. The B mode might be here. We know that it's not here, because we've been able to rule that out. Might be here, or might be here. We don't know. We don't even know if it will be detectable. And a bit of advertisement now that I'm coming to an end. This is exactly what people are focusing on right now, and that's what I'm working on. What we are trying to do is measure this component that we don't really understand when it's very bright, and if we get a really, really good image of it, then we can use it to try and basically subtract it from a map here and look for a signal in that case. And coming to an end, that's basically what will provide us smoking gun evidence of inflation, and that will basically rule out. Oh, Siri is listening as well. I'm glad. But yeah, that's what will give us smoking gun evidence of inflation, and what will tell us, okay, inflation did happen. There are alternative models that I would say I could get into them, but I could really not, because I'm not a big idea. All I know is that observationally, they haven't still predicted something that can be measured. The alternatives to inflation haven't predicted something that can be measured and have measured it. So they can predict many, many things, but if you cannot measure them, then are you really doing science? I don't know. But well, the conclusions, the first one, physics is cool. The physics is theoretical, but the fun is real. Serious conclusions. The theory of inflation is really I would say, the most solid cosmological paradigm that we have up to date to understand the very beginning of the universe. And there is a lot of effort put into looking for this signal that it's called a B mode. And the really, really takeaway is that we have no idea what's going on, and we've had this forever. Thank you.
Thank you, Pedro. We have about 10 minutes left for questions, and then we will wrap up at 9, although Pedro might stay a few minutes after if anyone would like to chat. We are recording the talk, so if you have a question, please raise your hand. We'll bring you a microphone, and please speak your question into the microphone so that the recording picks it up. So any questions?
One of your slides had that there was a false positive in 2014. How did that take over the physics world, and was everybody like, oh my god?
Oh, Woof. So in 2014, what happened is that the BICEP, this experiment of the South Pole, they had detected a B mode. So they look at the maps and they said, oh, we have a B mode. But what was happening is that the B mode that they had detected was coming from the galaxy. Basically, everyone that was competing with inflation said, oh, yeah, I think the most expensive glass detector is the cheapest. Which so far is true, obviously, but yeah, it was an interesting time to do it.
I have a question. I'm wondering what kind of data that you're working with, because when throughout your talk, you mentioned light and you mentioned temperatures. You're not physically taking any temperatures, right? You're going to be approximating it with something else. And I'm wondering also, I guess, just in general, like how are you measuring? How are you measuring, and like what kind of data are you looking at when solving your problem?
That's a really, really good question. So I use temperature and intensity as a table of and it's because in for this kind of we usually use something called light temperature. That is ultimately we are measuring with intensity. We are measuring how light is. But you can imagine voltage, and the voltage is just, if I get more light, I get more. I get that. So what I'm basically doing is I have a telescope here, and I get another. And there I get more than I get there. And if I say that my vector is linear, so if that's 5, that's 15, and if I get in between, I will go on that.
Hey Pedro, thanks for the talk. I just wanted to ask, how is CGEM going to help you with the foreground problem, given that you will always have some masses in the universe bending space and always polarizing the light from the CMB? Yeah.
So CGEM, CGEM is this experiment, the one that I'm. Thank you. Is the one that I'm working on for my PhD. CGEM is going to measure here, and we are targeting something called synchrotron radiation. That is just light that is cosmic rays coming from all over the universe. When they go through the magnetic field of our galaxy, they become polarized. And this radiation is not really well understood in the frequencies that we are looking at. You have different observations. There is a team in Spain measuring them, a team in South Africa that measure them, a team in California that measure them. If you look at what they measure, it's completely different. So it's one of them has done something wrong, or maybe all of them. So there is this knowledge of what is happening. You need to take measurements in many frequencies in order to know how this curve looks like. So this thicker line is the uncertainty that we have on it. In order to measure really well, you need to make of that super, super small. So what CGEM wants to do is we measure where the galaxy is really bright. We measure the shape of this. It's called the spectral index. We measure the shape of this curve. We use measurements at other frequencies. We interpolate them up. And we say, okay, we have a template of how this galactic component looks like. We are going to use it to extrapolate it here. That is where we expect B modes to appear.
So you mentioned all these sort of data that people have been collecting for the past, two, 3 decades, maybe more. It seems like a lot of data. So, like, how do you sort of get all that data and make that into prediction? Because it seems like unimaginable amount of data, because you're taking sort of pictures or videos of the entire sky for years at high resolution.
So what you do is, instead of seeing all the data that each experiment takes, you make a map. So you have your telescope. You can make a map every day. So let's say that you have your telescope always moving. The Earth turns once a day. You can make a map every day. The problem with that is that map will have noise, and will have noise is random noise, and it's noise that comes from your detector. So basically, just for the fact that something has temperature, there is this thermal noise coming from electrons in the material itself that are going to contaminate your measurement. So what you you know that noise is Gaussian noise. So if you take 300 maps, you bring down the noise level by square root of 300, I think it was, or a square root of 2 times 300. I don't remember exactly the expression, but you are basically bringing down the noise level. So every experiment produces a map, and that's how we just visualize. So there was this huge mission called WMAP, like 10 years ago. They were observing for 9 years. What people use at the end of the day is 7 maps. And in those 7 maps, you do all your analysis. Just by looking at, if you just look at this map, the thing with the cosmic microwave background is if you just look at this map, you can fit for basically almost all the history of the universe. There is so much information there that you just need that.
So when you're in the northern hemisphere and the southern hemisphere, the sky looks different. is what you can see in the telescopes different? Like, is it important to have telescopes on different sides of the Earth and like all around?
Yeah, that's a perfect perfect question. Actually, the experiments are happening in the South Pole, and I'm measuring the North Pole. So I see a completely different sky. That's really important. So when you're in the northern hemisphere, you can only see. Let's see if I have it here. If you are here, let's say you can only see up to here with a telescope, and if you have your telescope here, you can only see up to here. So that's really, really important. We are taking measurements in the northern hemisphere because we want to create a full sky map of it. So the goal is we create a map in the northern hemisphere. If it works and I get a postdoc, I go to Chile and I put it there. It's literally the plan. It's go to Chile or go to Australia, put a telescope there and measure. But it's really, really important. Actually, there is an experiment in Chile looking at this that we might overlap with, but other than that, not really. Sorry. Sorry.
It's not as good of a question as Aaron's, but what's the difference between inflation and like the Big Bang, or is that the same thing?
So when the Big Bang is this thing is this proposition that the universe began in a really hot state and cooled down. Inflation is the exact moment of this, when the universe was 10 to the minus 34 seconds old and just violently expanded. Nowadays, people usually talk about them interchangeably, and sometimes it's in inflation. It's basically by 95% of the community is seen as our cosmological model with our matter, dark energy, plus inflation.
Sorry, just could we see that like on that long one?
This one?
No.
Oh, sorry. Yes. Yeah, so this is what will be inflation, and the Big Bang theory is just, okay, it's the whole theory of we start from something really hot, it cools down and expands, but doesn't expand, like it's not this violent outburst. So there could be, in other words, there could be Big Bang without inflation, but there couldn't be inflation without Big Bang. That's really poetic. Wow. Yeah.